Alright, in today's lesson I want to look at the inverse function of the exponential function that we've been looking at the last couple lessons, and that is the logarithmic function. Now, you've seen some of this notation before, but I want to point out a couple of things related to what you see here in front of us. Notice we say the y equals the log base a of x. That's how we would read that. And this if and only if is basically telling us what this equation means. It means that y is the exponent of whatever the base of our logarithm is. And when we raise our base to that power, we will get x. Okay? Now there's a couple terms here that are helpful to understand here. Like I said, a is our base, but x, the thing that we are taking the logarithm of, is what's known as the argument. Okay? Now, the most important thing to remember about logarithms is that the solution to a logarithm, or what a logarithm equals, is an exponent. We are looking for an exponent, and that's why I have this bold and italicized and underlined and now starred. Keep in mind that these are exponents that we're dealing with. If you keep that in the forefront of your mind, then all the rules that we're going to learn and all the other stuff that we're going to do will make a whole lot more sense. Okay? Now, a logarithm is a function that takes a base and a value, which we call the argument, and it returns the exponent of the base that would give you that value. For example, down here, if you notice, it says x is the exponent of 2 that gives us 8. Alright, so if I were to translate this into an equation, I would say that x is, or x equals, the exponent. If x is an exponent, that means I must be taking a logarithm. Okay? Now, what is x the exponent of? Alright, basically here we're saying 2 to the x gives us 8. Alright, so we're saying that the base here is 2, and that the result, or the value, that 2 to the x equals is 8. So 8 is our argument. Alright, and I know it's kind of a backwards way of thinking of it from what we're used to thinking of it, but this is just how you kind of have to interpret it. If I see x equals the log base 2 of 8, that means 2 to the x power will equal 8. And actually, converting equations back and forth between these two forms is going to be an important skill that we're going to develop here. So let's look at exponentials and logarithms as inverses of each other. Notice here, in order to be inverses, they have to have the same bases. Okay? So here we have f of x equals b to the x. So here our exponential function has a base of b. So what we're saying here is that if we take the logarithm with the base of b of this original f of x, we will get x. Alright, in other words, the log base b of b to the x will always equal x. And if you think about it, that makes sense when we interpret it the way we just looked at. X is the exponent of our base b that will give us b to the x. Alright, so here our argument is what it ends up equaling. What the logarithm equals is our exponent, and our base is the base of our exponential. Okay, so you can see that, and we can convert that here. Here's an example as well, just to see the inverse operations that we have here. We have 10 to the x power equals 25. Well, just thinking logically, 10 to the first power is 1, 10 to the second power would be 100, and 25 is somewhere between those. So I know that x is going to be somewhere between 1 and 2, but I don't really know what it equals. Alright? So what I have to do here is I need to undo this exponential function. So I'm going to take the log with a base of 10 of this 10 to the x. And if I do that on one side of the equation, of course I have to be fair to the other side, and I'll take the log base 10 of 25. Alright? Now, what exponent of 10, here on the left side, this is what we're asking, what exponent of 10 will give us 10 to the x? Well, of course, x is our solution, because, again, these are inverse operations. So now all we have to do is figure out what the log base 10 of 25 is, and we can actually use our calculator, because on the calculator, if you remember, if you see log and there's no base written down, there's no base specified here, it's automatically assumed to be 10. Alright, so on the calculator, when you hit that log button, if we do the log of 25, we will get 1.39794 and so on. Okay, so you could say that's approximately 1.40 if we went to 3 significant figures. Now, like I was saying here with this, if we don't see a base written with our log, we automatically assume it's 10, and that's why we call that logarithm the common log. Alright? You see here, there are only 2 logs that your calculator can do typically, unless you have special functions to handle other bases. There are only 2 logs. There's the common log, that's a base of 10, and that's your log button on the calculator. But then we also have the natural log. If you remember, f of x equals e to the x, that was our natural exponential function. Well, a logarithm with a base of e is what's known as our natural log. So we actually use ln of x to represent that. And the reason why they bothered to put this one on our calculator is because of those applications we were looking at in our previous lessons. So many of them, when they were contiguous growth, had e to a power. So, for example, as we'll see later, if we want to solve for a time, the time was the power of e, so we would have to take the natural log. Alright, but let's take a quick look just to think through some of these logically. First of all, thinking in terms of a logarithm, if I were to take the log of 10 to the x, that of course would equal x, because I have a base of 10 for my exponential and a base of 10 for my logarithm. Now, if I'm going to do that on the left side, I have to take the log base 10 of 10,000. But if you think about it, 10,000 is actually 10 to the 4th power. Okay? So really we're asking, what exponent of 10 will give us 10 to the 4th power? Well, of course, 4 will. Okay? And we could do this with others as well. Down here, if I take the log base 10, the log base 10 of 10 to the x equals the log base 10 of, here I could rewrite this 1 over 1,000 as 10 to the negative 3rd power. Okay? So, of course, the log base 10 and the exponential with a base of 10 undo each other, so we have x equals, and then the power of 10 that will give us 10 to the negative 3rd is negative 3. And then finally, we also have the exponential function. This one we're not going to be able to figure out in our heads, but notice we have a base of e, so I need to take the log with a base of e in order to get x by itself. So of course I need to take the natural log of the right hand side. And since we can just plug that into our calculator, hit the ln of 10, we would get 2.302585 and so on. So we would say that's approximately 2.30 if we round it to 3 significant figures. Now, there are numerous applications of different functions that we can use that we would have to solve using logarithms. For example, all of the applications that we looked at in our last lesson, where we were investing money, or we had half-life, or if we had the depreciation of a vehicle, all of those, we were finding the value of the function, okay? However, what we never did ask in any of those applications was, when would something happen? And that's where the logarithm comes in, okay? When we're asking when. Here's a case where we're investing $12,500 at 7% interest compounded continuously. How long will it take for me to end up with $20,000? Okay, well, if I'm doing this, I need to use the right formula first, of course. So the amount at time t is going to equal the principal, or the amount at time 0, if you recall, times e to the r times t power, because this is compounded continuously. Alright, so if we plug in everything that we know in this case, I want the amount to end up equaling 20,000. Okay, this is the part that we were solving for last time. But now we know what the end result is supposed to be. And I'm starting with 12,500. Okay, that's going to be times e to the rt. So it's a 0.07 times t. Because we're asking what the time is. How long is it going to take for this to happen? So, we start to solve this. Before we can take any kind of a natural log, we have to divide both sides by the 12,500 in order to get the e by itself. So I have e to the 0.07t equals the 20,000 divided by 12,500, and I get 1.6. Okay? So, at this point, I have an exponential on the right-hand side with a base of e, so I need to take the logarithm with a base of e of both sides. And what that will do is now I will just have my 0.07t equals the ln of 1.6, which I can do on my calculator. And of course I need to divide both sides by 0.07, which if I plug it into my calculator, it's going to look something like this. So my time is going to be approximately 6.71 years. Okay, so if I leave this $12,500 alone and I earn 7% interest compounded continuously, I will have $20,000 after 6.71 years. And if you think about this, you know, this is going to be approximately 6 years and 8.5 months. Alright, so if we wait 6 years, 9 months just to be, we'd have a little bit over 20,000. Now, we can do this also with other bases. We don't have to just have e and 10, but we're going to look at the change of base formula in order to handle those later. For example, if this were compounded, say monthly instead of continuously, we would have had the equation, if you remember, the amount at time t is the principal times 1 plus, and you convert the R into a monthly rate, and you convert the time into, that would be divided by K, where K is 12. And it's to the T times K power, or we might have used N as well. Anyways, this would be 12. We would have 20,000 equals 12,500 times 1 plus that 0.07 would be divided by 12 to make it a monthly rate, and we'd multiply our time by 12 as well, because that's going to be a certain number of months, and our time doesn't necessarily say that we have to give our answer in years, but typically we would. Alright, but we'd start this one the same way. We'd have 1.6, and then we would simplify what's in the parentheses. We'd have a 1 plus 0.07 divided by 12, and we would have a 1.0058, and then that 3 would actually repeat to the 12t power. And what makes this a little bit challenging is not really the process, because the process is exactly the same as what we did right over here. We have a base, so we take the log with that base. What makes it a little bit of a challenge over here is that our base happens to be this 1.00583 repeated. So we're going to take the log with that base, 1.00583 repeated, of 1.6, and that will equal, if we do it on the right hand side, that will equal 12t. And of course at this point we haven't looked at how to do that log on the left with our calculator, but there's a simple way that we can do it and actually figure out what the time would be. So we can do this with any base, not just with E and 10. Alright, so go ahead and try the practice problems and see how you do.